Welcome to our next chapter. Now we are working with movements. We have two types of movements which we have to handle. Translations, these movements, and rotations. For these movements we have to define two things, positions and attitude. Attitude is your angular position or orientation in which direction we are looking at. But first, you will know everything is relative to something else, therefore we have to define coordinate systems. When we are talking about movements, rotations, positions, and attitude, we have to have a reference and say my position is relative to this or my attitude is relative to this. Okay, we are dealing with pose. This is decomposed of position and attitude. Our position is a three-dimensional vector. We are going to use Cartesian coordinate systems. So this is our Cartesian coordinate systems, and you will see our position will have three components. One for this axis, one for this axis, and one for this axis. Exactly the same when we are movement. Our movements will be relative to some kind of reference system. And now we are talking about rotations. The rotations will be what we are dealing around one of two or all three these axes. So everything which we are dealing are three-dimensional vectors for position, translations, attitude, and rotations. Now let's define a few things. First, as I said before, this is our pose. And the pose is the composition of a position where I am and my attitude, in which direction I am looking at. Then if we move, we are going to change our position, and that is delta position is the translation. If I am rotating, then delta attitude, my orientation will be my rotation. And if I am doing both, the delta pose is going to be the translation plus rotation. Plus, please do not confuse the delta with the speed. The delta is I was here and now I am here, then the delta was this step from here to here. My speed is a function of time, and we are going to use differential equations. So the differential of my position will be my speed, the differential of my attitude will be my angular velocity or rotation rate, and the differential of my pose will be both together, my speed and angular velocity. Okay, now let's begin with positions, where I am. If I am defining where I am, I said before, I have a relative frame. If I am this room and I ask you where I am, for sure you are going to describe my position relative to this room. In this case, we are going to define the coordinate system in this room. Let's say x is looking in this direction, the y vector is looking in this direction, and the z vector is looking to the top. So I will have a coordinate, and you will see where I am. Now we have the first problem. If you tell me where I am, you are maybe make very precise measurements, and you can tell me where I am with plus minus 1 centimeter, with accuracy of 1 centimeter. Plus I am bigger than 1 centimeter. So when you are talking about my position, you are not talking about my whole body, you are talking about only one point. And if I move my head, then let me ask, I am changing my position or not? Or I am moving my arms. According to where is this point where you define my position is changing or not. Maybe you will take my feet as reference and to say where I am on the ground, then I can move the rest of my body as long as my feet are in the same place, I am not moving. But if you take, for example, the center of gravity of me, this is somewhere here, then when I am moving, the center of gravity is moving, then my position will be changing. Another example of relative position is, let's take my keyboard. Here is my keyboard. I can ask you, where is the A taste? If you describe where is the A, maybe you will use a coordinate system which is relative to my keyboard. You will say according to this corner or to this corner. So if I am moving the keyboard, the key A is moving too. But your description, where is it, will not change. It's still the same because the reference is moving together with this key. So let's take this differentiation. What occurs if my reference is moving, or I am moving, or we are moving together? We are going to have many different of these reference systems. Let's take an example. This. Look at these three persons. Do they have the same attitude? What will you say? I think you say they are all three standing. Of course, they have the same attitude. But let's take another reference system and you will see they don't have the same attitude. Here in the center is the Earth. And then look at these three persons again and you will see they have a different attitude. He is standing, he is on his head, and he is lying, for example. And if I consider my position here, I will stay here as long as this lecture lasts, maybe 2 hours. Then I will be rotating together with the Earth. So my attitude at the beginning will be like this. And after 2 hours, the Earth is rotating 50 degrees per hour. My attitude will be something like this. But if you take the Earth as reference, then I will stay always in the same attitude like here. I am sitting or I am standing in a vertical way. So my attitude is not changing all this time. But if you take something far away from the Earth, for example, stars, then from the stars you will see I am rotating together with the Earth. An example is the same with you. Let's say this is your attitude at the beginning of the lecture. What will be your attitude at the end of the lectures? You will be rotating, but I hope your attitude will not be like this. Your attitude will still be active and paying attention, even if you are rotated. Well, that is a game with words because the word attitude has 2 meanings. But what I am meaning is only my angular position when we are talking about attitude. The same example, now let's see these 4 airplanes. I will place the Earth here and then they are going to have a different attitude. But let's take a reference, this star. If we are looking from this star, for example, Polaris, that is in the same rotation axis from the Earth, then all of them have the same attitude. So when we are talking about attitude, we have to say attitude relative to what? To which coordinate system? Of course, the Earth is most of the time for reference coordinate system, but sometimes we use the stars. And the attitude is different according to what we are using. Be aware. Another important thing is our reference system can move. Just a second. This will be our reference system, and we will have, in this case, we have only 2 dimensions, 2 vectors. This is the x vector and our y vector. So our position will be relative to these 2 vectors. And if you take a look, you will see the position is here, 2 units in this direction and 3 units in this direction. So we say our position is 2, 3. This is it. But now let's assume this point stays in the same position. Oh, sorry. Do you see? It stays in the same position and the reference coordinate system is moving, is rotating. Then the coordinates are moving. But now I say this point stays in the same position from here to here. Now tell me, relative to what is standing in the same position? Relative to my reference coordinate system, which is your display. In your display, this point is not moving. But in this coordinate system, the point is moving. So my new coordinates are 2 in the x-axis and 0 on the y-axis. This is my new position, even if relative to other reference system, my point didn't move. Let's see something different. Let's see distances. Let's take 2 points, this point, and we subtract the coordinates. Then this is at 1, 1, and that is at 6, 1. So the difference will be 5 units. And this is our distance. And what will occur if we rotate our coordinate system or we move our reference coordinate system? Then we can have something like this. The coordinates, the position is now different. This is still 1, 1, but that is now 4, 5. So the coordinates have changed, but the distance shall stay the same. And if we make some computations, you will see the distance in x from here to here is 4, and the distance in y from here to here is 3. So, do you know the Pythagoras triangle? So you make 4 square plus 3 square, and then the root of 4 from that, and it will be our distance, and this is 5. So, our distance from these 2 points didn't change, even if our reference coordinate system is moving, rotating, or experimenting some translation. So be aware of these topics. And now let's assume I am rotating everything. I am here at this point and I am observing the world from this point. So if my coordinate system rotates and I am rotating with this, I am not going to be aware of this, and this is what I am going to see. The new position of the new position of these two elements with this task, and the distance is still 5, like before of the rotation. Okay? Okay, now I said we have different coordinate systems according to what we are doing. I'm going to list here a few. For example, if we can use the Earth surface as reference if we are looking for things which are attached to the Earth. For example, the address of my office or my flat where I am, maybe you shall use the Earth as reference, or a city or something like this, and the city is moving together with the Earth. But if we are in orbit outside of the Earth, then we don't care about the rotation of the Earth, because our movement around this point, the center of gravity of the Earth, is independent of the rotation of the Earth. But we are moving together with the Earth around the sun. And then we have another coordinate system. This is the Earth inertial coordinate system, SE. And SE is defined. The center is in the center of the Earth, and it is moving with the Earth, but it is not rotating. The definition of its vectors is something different. I'm going to come to this later. I could have something different, for example, a coordinate system relative to my labor. If I building something in my lab, I should say where is it relative to some coordinates in my lab. Or something very important but very difficult to define is if I am flying in an aeroplane. To keep the aeroplane flying, I have to know the relationship between me, the aeroplane, and the surrounding air. If the surrounding air is moving, then I shall be moving faster than that, else I can fall down. And therefore, another reference system could be the air around me. Plus, I said before, to define this coordinate system will be very difficult. Or if we are flying from planet to planet, then we shall forget about the Earth and have, for example, the Sun as reference coordinate system, or the stars. Or, for example, if we are flying to the Moon, maybe we shall change from Earth coordinate systems when we are departing to the Moon coordinate systems when we are arriving. So we can change coordinate systems. But something very important, if we are building something, I have a device and I am constructing this device, then my coordinate system shall be relative to the structure of this device, to know where the screw on bow or plug or something like this, in which direction relative to this box. So this is what we call the structural coordinate systems. For example, what you see here, you can see here you have instructions where to plug the screws, where to build this component and so on, and they are all relative to the box where you are building your system, or the structure of your system, whatever it is. Okay, then how to define the coordinate systems. In a coordinate systems, Cartesian coordinate systems, what we are going to use, the first thing we have to define is the origin, where the coordinate system begins, the point 0, 0. And this will be, for example, if I am the front of my nose, my feet, the center of gravity, or something different. For example, if you take this cube and you want to build something, maybe you will see the 0, 0 is in the center, here, and the bottom, for example. Then the next step is to define these three vectors, the x, y, and z vectors, in which direction they are looking at. Let's take, for example, this surface here. You could define, okay, my origin will be here at this corner, and then we have the x vector looking in this direction, the y vector looking in this direction, and the z vector orthogonal to this spot, orthogonal to this surface. Okay. And something very important, these three vectors shall be orthogonal. We can work with not orthogonal vectors, but this makes everything much more complex. So let's do it, think simple, and keep these three vectors orthogonal. Okay, if they are orthogonal, then we have to define only two. And I hope you remember from your mathematics, if you have two vectors which are orthogonal, and then you multiply them with a vector product, cross product, then you are going to get a new vector, a third vector, which is orthogonal to both of them. So if you multiply these two vectors, the result will be this vector. If you multiply these two vectors, the result will be this vector. So you have to define only two vectors, and the third will be used the computation, the cross product of the two vectors which you have defined. In this case, it's enough if you say x is going in this direction and y is going in this direction, and then you can compute what will be z. Okay. Another important, not only saying where are the vectors under which is the plus direction, in which direction is growing, and which is the minus direction of each vector. For example, you can say the z vector is vertical, but you have to say going up or going down. So in this case, you have to define where is z minus and z plus. You will think most of the time z shall point to the top. So when increasing z, you are flying high, and when decreasing z, you are falling down, for example. It's naturally, but there are many coordinate systems where they use the opposite. So do not be afraid about this. And now there is a convention which we like to use. To make everything simple, we are going to use colors. Red will be X, green will be Y, and blue will be Z. And this is what I am using here. I wanted to use these colors, but I have a small problem. Here I am using a green screen, and my system is doing everything which is green to black or to transparent. Therefore, you cannot see the green vector. Then I have to substitute the green vector by some other color. I am using yellow. But try to remember, actually, this shall be green, the green color. Something like this. Okay. And now, how to define the coordinate system? I said an example. We have to define these 4 parameters or 3 parameters. First, the origin, and then at least 2 of these vectors. In aeroplane, for example, it will be, if we are flying, the center of gravity could be the origin, because all rotations of movements are around the center of gravity. But if we are building the aeroplane, then to have the center of gravity as reference is a bad idea, because as we are building and changing the structure of the airplane, the center of gravity is moving. Even when we are flying and consuming kerosene, which are stored on the surfaces here, on the wings, then the center of gravity will move. So take care what do you need before you define your coordinate systems. Or for example, in my office, we could define the 0 point, one corner of my office, and then everything will be relative to this. I said before, on the Earth, for example, we could define the center of gravity to be the 0 point, and then we have to define what is X, Y, and Z. A very common definition of Z is the rotations axis of the Earth, which is almost the magnetic North Pole. But you shall know the magnetic North Pole is not exactly on the rotations axis of the Earth. When you are getting coordinates from GPS or something like this, then your North Pole will be this rotations axis and not the magnetic rotations axis. Be aware. So most of the time we don't use the magnetic North Pole, we use this rotations axis. Okay, we have defined one vector already. Then we have to define the other 2. We will come later how to define them. And now come back to the aeroplane. How to define this? Most of the time we define X to look to the front, Y to look to the right, and Z to look to the bottom, down. And this could be a surprise. Why? There is a reason to define what is a positive rotations angle and negative rotations angle, and it is better for these definitions of positive rotations if the Z vector is looking down and not looking up. There is something more which I am going to explain in a few seconds. Okay, then we don't need, it's not enough to say we have 3 vectors and in which directions they are looking at. We shall take care to have a right-handed coordinate system. So take your right hand and say this will be 1, 2, 3. This represents X, Y, and Z. And you can rotate this but you cannot mirror this. If you take your other hand, by rotation you cannot attach or make but to point all three vectors in the same directions. They will be always different. So we can, when building the coordinate systems, we could do something like this, or we could invert this vector. Plus in this case, I cannot build, this is x, that is y, and this is z. I cannot bring it together with my right hand. So I have to interchange these two. Oh, sorry. And then I can have this x, y, and z. Okay, according to my right hand. And this is very important because we have to build a mathematic, and this mathematic has to know what is the structure which are we using, and it shall be always the same, looking like this right-handed coordinate systems. If you invert this, then you have to change a lot of formulas which are handling movements and translations, and that will be a very terrible situation. So the most simple way is to define this standard and keep this standard and build the mathematic on the top of these standards. So be aware. Okay, now how to define a point. Let's say, for example, I have this point, and this point has three coordinates, is in this coordinate system. This coordinate system could be, for example, inside of my satellite, of my aeroplane, some part of the aeroplane, then I shall say, where is it? If I am building the aeroplane, it will be nice if it has a relative position to the structure of aeroplane. If I am flying and I have a camera and I would like to know in which direction I am looking at, maybe it will be better if we use the Earth as reference. But let's forget about this now. We have a reference coordinate system, and we are going to define everything relative to this reference coordinate system. Okay, maybe you know from the school, you defined a point in a three-dimensional world like a sequence of three scalars. The first one represents the position in x, which is going to be this. The second one, the position in y, which will be this. And the third one, the position in z, which is going to be this. Okay, you can write the point a vector like this, or you can write your point in a vertical vectors, for example, if you are multiplying by matrices. But at the moment, it makes no very big difference. We can do it a little bit more complex, and you will ask, why are we doing it more complex than required? But later you will see there is a good reason. You can define three vectors, three unity vectors. We can define the x vector to be 1, 0, 0. You can define the y vector to be 0, 1, 0, and the third vector to be 0, 0, 1. And these are these three vectors. These are the coordinates of these three vectors, and these are the coordinates of this vector relative to something else. Let's say our reference coordinate system, and this is our body. Our body is moving and rotating, but the reference coordinate system shall stay the same. So all movements and rotations will be relative to this coordinate system. So when we are moving our body frame, which is this, then these coordinates will change. But at the beginning, they are the same like the reference coordinate system. Okay, we will see how it will help us. Then let's define the position of this point is relative to these three axes. So we take the first element and multiply by the x vector, and the second element multiplied by the second vector, and the third element multiplied by the third vector, which is the z vector. And now the definition of our point is not just this sequence of these three scalars, but the multiplication of the first scalar times this vector plus this vector plus this vector. So as long as they stay like they are, it will be exactly the same, because we are multiplying by 1, and then we add this by 1 here, and then we add this by 1 here, and then the result will be exactly this. But this is true as long as we have not changed the position or rotation of our body coordinate system. Okay, but now remember, we can move our coordinate systems. At the beginning, red was looking in this direction and green was looking in this direction, and now it has rotated. And if these 2 points are fixed to this body, then relative to this coordinate system, they didn't move. They have still the same coordinates, but relative to the screen which we are looking, now they have another attitude, another position, another coordinates. But relative to this are the same. But this, we are going to handle this later, which more time. And this is a small exercise to you. Take your right hand and let me know, is that right-handed or not? Try. Well, I'm going to say they are not right-handed. If it is not right-handed, you have two ways to transform from left to right. One of them is just to invert one vector. If this vector was looking in this direction, then make it in the other direction, and then you have changed from left to right or from right to left-handed. The other way is just to interchange two vectors. For example, these two. Now we have a left-handed coordinate system, which we are not going to use. And now we rotate back, we transform back, and now we have a right-handed coordinate system. If you take a look to these three are right-handed. You can bring to match with your right hand, but this not. So you have to transform, interchange two vectors, or invert one of these vectors. Okay, and now another important thing is, if you want to draw something flat, it will be difficult because you are not sure in which direction this is looking at, in which direction. So there is a convention how to draw three-dimensional drawings flat. Okay, and these are the two vectors, x and y, and then here we have the set vector. We can define a circle with a point or a circle with a cross. If we say a circle with a point, then this vectors begins here and is looking to you. So from the screen to you. You are on the positive side and the screen is in the negative side or the paper. If you use a cross, then this vector is looking in the other direction. It's looking from you to the screen. Exactly the same to remember. If an arrow is flying to you, then you are going to see a point for the last time. And the arrow is going away from you, then you are going to see the back side, and this shall be something like a cross. Just to remember when to use a point and when to use a cross. Okay, and this is how, only for drawing, how to draw three-dimensional coordinate systems on a flat. Okay, now I said before, we need different references. We can have a reference, the center of the earth, the sun, something else, or one person, or the aeroplane. What to use depends on what you are doing to do. Okay, these are the three different things which we have to handle. The body coordinate systems, they have Zumbashville the structural frame. I said before, you can define, okay, here, this point is the zero position, and then you can define x, y, and z. Or the mechanical coordinates frame, if it is rotating, then the center shall be the center of gravity. Or principal axis, I'm going to come to this later. But this coordinate system, all of them are body coordinate systems, and they are fixed to your structure, which is moving, then this coordinate is moving. Then we have another relative to Earth. They are fixed to the Earth. We have the Earth center, Earth fix, SF, what I mentioned before. And this is in the center of the Earth and rotating together with the Earth. What we see if we are fixed on the Earth. Another important is the Earth center inertial frame is moving with the Earth, but it is not rotating to the Earth. The axes are fixed in space. Okay. Or if we want our coordinate system relative to orbit, then we have move with our satellite or spacecraft and then define the coordinate system relative to the orbit of this spacecraft. For example, one vector is looking at the sun or at the Earth, other in the moving speed or orthogonal to your orbit plane. Okay, we are going to handle this later. But remember, these three groups is very important to keep in mind because we are doing a lot of things with body coordinate frames, Earth coordinate frames, and orbit coordinate frames, and we shall be able to transform any point from here to here or to here, other in other direction. And the transformation is nothing more than a translation and a rotation. Okay, but there are two very special frames. The inertial frame, which is independent from the universe. That is something very important. And the delta pose. The delta pose is what I use, for example, for relative navigation. If I know what was my position and my attitude at the beginning, and then I am moving, I keep integrating all my movements, and then I can compute what is my new pose. And remember, the pose includes the translation and rotation. So I am protocolating here all my translations on all my rotations, and I can have my new position relative to my first position. So we don't have an external coordinate frame. We are having only this relative to my original position. Or inertial, independent from the rest of the world, of the universe. Well, we have here a nice thing. Einstein said everything is relative, but really everything. And we have here an exception, seems to be an exception. The inertial coordinate system is relative to nothing. So we can remove all matter, we can remove all universum, and two things can still be measured independent of the rest of the universum. One is the acceleration, changing of speed. We cannot measure of speed because our speed is relative to something else, to the street, to a star, to the ground, who knows what. But the acceleration is independent of anything else. And the second thing is our own angular rotation, angular rate, rotation speed. Even if we remove the universum, our rotation speed can be measured because we don't need any relative thing for this. And these are the two very special coordinate systems, the delta pose and the inertial coordinate system. Okay, the inertial pose, I mentioned it already. And now let's see some examples of body frame or coordinates systems attached to the body. The aeroplane I mentioned before. And now, a surprise, you will expect ships are very similar to aeroplanes, and then you will expect the ships to find the coordinate systems like the aeroplanes. But look, it's different. X is looking to the front, like the aeroplane, but Z is looking to the bottom. Here, Z is looking to the bottom, to the top. And remember, if we interchange this, then we have to switch the other vector too. Here in the aeroplane, Y is looking to the right. In the ship, Y is looking to the left. Else, it will not be a right-handed system. So, if we change one vector, we have to change a second vector too. In cars, we have something different, a very special situation. For example, in German cars, from manufacturer to manufacturer can be something different. In German cars, X is looking to the back, and Z to the bottom, and Y to the left. But if you look in Japan, it will be something different. So be aware. And very special case are the satellites. For satellites, there is no standard. So every satellite builder defines its own coordinate systems as he wants. So be aware when you are working with satellites. First ask what is the definition of the coordinate systems, else you can make very big mistakes. And launchers are something very special too. They are flying like an aeroplane and they can be in space. You will expect maybe that the Z vector is looking from here, to the top. But it will be a surprise if you look at the definition of the coordinate system of this launcher. X is looking to the top. So you can define the movements of a launcher, something relative similar like the aeroplanes. The aeroplanes, the X is looking to the front. And even if this is the top, they are flying to the front. So you can define the movements of a rocket like roll, pitch, and yaw, exactly the same like an aeroplane. This is if you define the coordinate system relative to like an aeroplane. And this is maybe for many of you a surprise. Many of you will expect Z to be in this direction, but Z is in other direction. Okay, and now another definition, coordinate systems around the Earth. I said before, we have a coordinate system which is moving together with the Earth, but it's not rotating together with the Earth. So the axes are defined somehow different. But before I mention this, I wanted to mention the coordinate system SF, which is rotating together with the Earth. Okay. The center of gravity is the origin of the coordinate system. Z is the rotation axis of the Earth. Then we have to define one more vector. The second is only the multiplication of the two already defined vectors. And this one vector is defined by the intersection from Greenwich meridian, 0 meridian, with equator. So if you make a line from center of the Earth to this point, then you have the X vector. The Z vector is the rotation vector, and then you multiply both of them, and then you get your Y vector. And this is somewhere in India or in southern from India, in the Indian Ocean, is the Z coordinate. Okay. And now the other case, and this is rotating together with the Earth. The meridian is rotating and the equator is rotating together with the Earth. But now the Earth center inertial fix, which is moving with the Earth but not rotating with the Earth, it has to be defined somehow different. Okay, first, the center is the center of the Earth, it's okay. The Z is the same rotation axis of the Earth, it's okay. But now we have to define what is X. And let's take something very special. You can take a star and say, okay, X will point always to this star. And then it doesn't matter how the Earth is rotating, the coordinate system is moving together with the Earth, and X will be always pointing in this direction and Z in the other direction. So they will not rotate together with the Earth. But they define this in other case, in other way. For this definition, we take the equinox. I don't know if you know what is equinox. An equinox is the day, actually it's less than a day, where the sun points directly to the equator. So the duration of the night is exactly the duration of the day. If you live in the north, very far in the north hemisphere, or in the south hemisphere, you will see there is a very big difference in the daylight and night light between summer and winter. If you live close to the equator, then you will not be aware of this difference. Okay, let's take this. The Earth has, the rotation axis of the Earth has an inclination about the ecliptic, and the ecliptic is the rotation around the sun. But it's constant. It's not rotating around the sun, it will be constant. So when we are rotating around the sun, this axis will stay the same. So it points, if we prolong this, to a star which we call the polar star or Polaris. And this is the same if we are on this side of the sun or on the other side of the sun. And in this case, take a look, if we make a line from the center of the sun to the center of the Earth, in June, this will be about equator, and in December, it will be below equator. Okay, if in June is below equator and December is below equator, there must be a time point where this vector goes exactly to the equator. And this is when the Earth is here, in the front on the sun. Here we are moving like this, and in this moment, the vector going from the center from the sun to the center of the Earth cross exactly the equator. And then we take this point to define the X vector. And the X vector is going from the center of the Earth to the center of the sun, crossing the equator exactly in this moment, in the equinox moment. And this is somewhere in March. But we have another problem. It's not constant. Just a second. If you take a look to this table, sometimes it's a few minutes earlier, sometimes a few minutes later, so it's moving. So to define this vector, we say it was on 20 March in the year 2000. And we keep track in which direction this vector was pointed. Of course, there shall be a star there. And this is what we are using as the X vector. Okay, X and Z are defined. Then Y, we multiply these two vectors, and then we get the third vector Y. And then we have defined our inertial coordinate system on the Earth. So they will point always in the same direction, They are moving with the Earth, but they are not rotating with the Earth. Okay, and this is the definition. This is the rotation axis of the Earth. That is the rotation ecliptic plane, the rotation of the Earth around the Sun, and this is the where these vectors are pointing to. Okay, if you think we have already many coordinate systems, then take a look to this. These are some of the coordinate systems we have to handle when we are working with satellites. There are really many. We are going to see maybe only 3 from each group, and it's a note. And from these 3, you shall know how to convert from one to any other. It doesn't matter how to define the coordinate systems. And now we have something, mounting frames or transformation from coordinate systems. For the transformation of coordinate systems, you shall know 2 things, the rotation and the translation. And then let's say we have here a chain of coordinate systems. We have, for example, overlap, and overlap has a position on the Earth. So the definition where overlap is relative to the Earth as reference frame. And this reference frame shall rotate together with the Earth, so it's the coordinate system called SF. Okay, if we are building something in the lab, then of course our coordinate system shall be relative to the lab, and they are fixed to the Earth, but we are not going to use addresses to say where is my satellite in the lab, or where is the robot, or where is the camera. We are going to use coordinates which are relative to my lab. Okay, then in this lab I am building my satellite, and it is in some place. I want to know where, then I can define relative to this lab, and inside of the satellite I am building some other components. For example, cameras, star sensors, wheels whenever we want, computers, and each of them will have a fixed position where to build and a fixed orientation. I say not only please place the camera in this position, I have to say place the camera in this position and with this orientation. The camera should look in this direction. Okay, and this is of course, all these construction instructions are relative to the body frame of my satellite. Even if I move my satellite around the lab, these coordinates will not change. Do you remember what I said before? If I am moving my keyboard, the definition where the A key is will stay the same because it's using the keyboard as reference. Okay, and now we have, for example, a roboter. This roboter is fixed at some point in my lab. So we have the coordinates and orientation of the basis of the robot. Then we have an end effector. This is the hand of the robot, and this is moving to catch something. Then we have a transformation of the position and pose of the end effector relative to the basis of the robot. And if I want to know where is it relative to the lab, then I have to convert from this coordinate system to this, and from here to my lab coordinate systems. And then maybe I have something in my satellite which shall be taken by the robot. So I have to make a coordinate transformation from the end effector to the base of the robot to the lab, then from the lab to my satellite, and from my satellite to the part which shall be the target of the base. And then I know the relative position of the end effector to the target which it shall take. So as you can see, we have a chain of transformations to know the relative position of this to this. On another example, I have somewhere a camera with a lens. So the camera shall move, and I shall know the position of the camera and the position of the lens to know in which direction the camera is pointing at, what I am looking at. So if I want to move the camera to point to the satellite or to rover, I have to make this transformation, the lens from the camera to the camera, then the position and attitude from the camera to the lab, and from the lab to the base or to the end effector, according to what I want to see. And then I can compute the relative pose of the lens to the end effector. And then I can see I am looking in the direction which I want to look, or I am looking in other direction. Okay, now you see all these transformations which we have to do, and each transformation include a translation and a rotation. Another example of mounting frames where I have to see the relationship between coordinate systems is when I'm building, for example, my satellite. Here in this example, I have a sun sensor. The sun sensor has a sensor which tells me in which direction is the sun. For example, let's assume this is my sun sensor and the sun is in the front, then it will tell me a vector which tells me the sun is looking in this direction. This can be the same, but if the sun sensor is rotating, then this vector relative to the sun sensor will be changing. And this is the only thing the sun sensor knows, the vector, the light vector relative to himself. He doesn't know where the Earth is, he doesn't know the structure of the satellite, so when you ask where is the sun, it will deliver a vector which is relative to himself. So we have to know what are the coordinates of this sun sensor, x, y, and z, because the vector which is going to deliver are relative to this frame of this sun sensor. And now in a satellite we have more than one sensor, maybe 6 or maybe 8 or even more. And they are not mounted looking in the same direction. Of course, if all of them will look in the same direction, we need only one. And the other will be in shadow, for example. So one shall look to the front, one shall look to the back, to the top, to the bottom, to the right, to the left. This is a mistake, what I said. With satellites, we don't say front, back, top, bottom, because there is no front, there is no back, there is no top, there is no bottom. We say plus x or minus x, plus y or minus y, or plus z or minus z. So we have to know where they are mounted. So here you can see in this direction we have many of these sun sensors, and if you take a sharp look to here, you will see the orientation of the coordinate systems is not the same. They are looking on different directions. So if you ask then and then where is the sun, you are going to get different response because they are looking in different directions. So this will say the sun is in this direction relative to himself. The sun is still in the same direction, but the other is mounted something like this, for example. Then relative to this is another vector. And to know where is the sun relative to you, to the satellite, then you have to convert this vector which says the sun is in this direction to this mounting frame where you know how did you fix this sun sensor to your satellite. And the same with all 6 or 8 sun sensors according to how many do you have. And then you might continue. You would like to know if the sun is in this direction, where is the Earth? So you shall transform this vector, the sun vector, relative to the satellite, and then relative to the Earth. So, you know, a lot of reference system transformations. This is what we are doing. Okay, and now if we are talking about mounting frames and how to transform from one frame to another frame, let's take a look to navigation frames. We mentioned this already. We mentioned already body coordinate systems, which are fixed to the body, to the aeroplane, to the drone, to the car, to the satellite, who knows what. Earth, SF, which are rotating with the Earth, SE, moving with the Earth, but not rotating with the Earth. And then we have the navigation systems. We have the N, which is the orientation or navigation coordinate system. We have the B, which is the mechanical body coordinate systems. So it's fixed to the car or to the aeroplane or what you want. The inertial, what I explained before, they are from the inertial coordinate system. We can measure only acceleration and rotations, and we have no reference to the rest of the world. We have to make a transformation how we mounted the sensor in our structure. And then we have the Earth coordinate systems, which are relative to the Earth. Of course, we are talking about navigation of the Earth, then it shall be rotating together with the Earth. So for the A frame, we use the SF, which is this. For the E frame, the sogenannte inertial frame. To the body frame, the mechanical frame. And for navigation frame, the orientation on Earth. And maybe you will think N and E could be the same. they are relative to the Earth. But you will see they are not the same. Here, A, its origin is the center of the Earth, and Z is pointing to the rotation axis of the Earth. N is where I am. The origin of N is this position where I am, and Z, or not Z, X is pointing to the north. And then you could think my X from N shall be the same like Z from E. Is it true? They are both looking to the north. Then, shall they be the same or not? They are not the same because their origin are different. So even if they are looking at the same point, they are looking from different directions. So they are not the same. This is looking from here, and this is looking from here. As you can see, these two vectors are not the same. Okay, let's see. Here we have all these three navigation frames together. We have the Earth, the E frame. Here is the Z. Do you remember the definition of X? And do you remember the definition of Y? Then we have our body frame. In this case, a car. Okay, we defined our coordinate system relative to the car. X is looking to the front, Z to the top, and Y to the left in this direction. Yes, and the origin is this point. Oh, you can define any point. Okay, and this is your car. And the orientation of your car, it can be looking at any direction, who knows where. So, and this is not relative to the car, but for example, for the navigation frame. And here you can look, the navigation frame, the origin of the navigation frame is the same origin of your coordinate of your car. So you are in the center of this frame. X is looking to the North Pole, but look, these two vectors are different. And this can be moving. It can be an equator, or it can come in here, and when it is almost here and the North Pole, then they are going to be almost orthogonal. So they are changing. And when they are an equator, they could be almost parallel. Almost. Okay. And then you define Y to point to the east, and Z to the top, and this to the north. And all of them are orthogonal. Okay, and then if you want to know where are you relative to your navigation frame, this is what you need. If you know, for example, 3 blocks to the front and then 2 blocks to the left. All of this is relative to this frame. You don't know the rest of the Earth. But you would like to transform from this frame to the Earth and to your car. Okay, now we have these transformations. This is what I said before. Then we have, for example, any parameter, for example, position or speed. In this case, we are going to use the speed. If I say what is my speed, I shall say relative to what? Then I said my parameter, speed, and then I said relative to which coordinate system. If I am in the car and I am moving inside of the car, maybe my velocity is important to the other parts in the car. Or in a bus, on a train, maybe my velocity is relative to the train and not to the ground, because I am moving inside of the train and this is my world. Okay, in this case, maybe we are moving the car and we say this is our velocity relative to the end frame. That is the navigation frame, do you remember? Okay. And now we can have transformations. If we transform, for example, or velocity from a frame A to a frame B. For example, the frame A could be, I am in the train, which speed do I have relative to the train, and then which speed the train has relative to the ground, and I would like to know what is my speed relative to the ground. Then I have to make this transformation from me to train, from train to ground, or from car to ground. It's not just adding, it will be in different directions. Maybe the train is moving in these directions and I am walking in this direction. So the transformation is somehow more difficult than just adding speeds or position. Okay, so my representation will be like this. This is my parameter, velocity, and the transformation from A to B. Or I can write, it's exactly the same, my parameter, velocity, from A to B. Okay, here is the transformation. Here is the value. My speed in this frame. And here is how can I transform my speed from this frame to this frame. So this is an operation. And there is something, this is transitive. For example, if I am going to transform from A to B, but I don't know the direct connection from A to B, but I know, for example, from A to E, I can translate from A to E and then from E to B. So, here it is in the ground position, so it's the same, the transformation from A to B, like the transformation from A to E, and later the transformation from E to B, for example, for speed. Okay, up to now we were talking now only using Cartesian coordinate systems. This is because all mathematics which we are using is based of Cartesian coordinate system. We can use other representations, for example, cylindrical or polar. Maybe you remember the definition of this, but we don't need this. Polar, we need this because some positions of the Earth are defined as polar coordinate systems. So we have to know how to transform from Cartesian to polar, but I hope this is something you remember from the school. I'm not repeating this here. But why do we need polar? It will be much better to do everything with Cartesian or everything with polar, but these conversions, it makes more work. What for? And the problem is many positions of the Earth are defined with polar coordinate system. So you say your longitude on your attitude. I hope you remember the definition of these points. And then you shall be able to transform from latitude and longitude to x, y, and z. And remember the definition of x, y, and z, and the definition of these angles. This angle, the longitude angle begins at Greenwich meridian, 0 meridian 2. And this, the latitude, begins at equator and is growing from 0 to 19 and from 0 to minus 19. Okay. And now I wanted to show you some body coordinate systems. We have mentioned already so many of them, so let's make some clear examples. I said before, there is no standard for satellites, so this is only an example. Another satellite builder, another constructor could use a total different coordinate system, definition of coordinate system. In this case, the builder of this satellite said, my origin is here, in the center of the bottom plate. This is the structural coordinate systems, where this is the coordinate system which you need when you are building something in this device. Okay, and then he defined, here you can see the definition of the y, the x, and the z and the x, saying what is the minus, the plus, and the plus direction. In this case, let me see, z is looking from here in this direction. I cannot see it from here, the color are bad, but I think x is looking from this direction in this direction, and z and y is looking in this other direction. So when you are defining the position of any device, it can be relative to this point and these three directions which I have defined. Other builder will say, no, the center shall not be this here, the origin shall be, for example, this corner, which I will prefer, is better to measure. Okay, but that is pure constructions. For rotations, it's different. When the satellite is in orbit and it is rotating, it will not rotate around this point. It will rotate around the center of gravity, which is somewhere here. So we have another coordinate system, which is for rotations, and this is the mechanical coordinate system. And you can see the definition of the axis is still the same. They are looking at the same direction, but the origin is not anymore here. It is somewhere here in the center of the satellite, where is the how do you say, center of mass and center of rotations. So it is used shifted. Use shift is not so difficult to compute the transformation of coordinates. Okay, but now we are handling with rotations without control. Rotations without control are rotating about the main inertial axis. And the main inertial axes are not exactly the same like the structural axis of the satellite. They will be different. For example, if you take, no, that is a bad example, because the inertial axis will be along this. Also, this is a bad example, forget it. Okay. Okay, I said before the center of gravity is again the origin. So this is a common point between the coordinate system, the mechanical and the principal axis coordinate system. But the definition of the axis will be different. This is the tensors, the inertial, the maximum inertial of momentum of rotation of the satellite. So you can find this and the second one, and the third one is the cross product of these two, the first rotation axis and the second rotation axis. Okay, and now we have the Earth coordinate systems, but the transformation from Earth's fixed, which are rotating together with the Earth, and Earth inertial, they are very complex. So you know there are mathematical formula how to transform from here to here, but we are not going to handle them here. You can take a look to this later if you want. Okay, but I wanted to show only the definition. The inertial coordinate system, do you remember, is in the center of the Earth, but this X is looking to the the vernal equinox in year 2000, and Z is the rotation axis of the Earth. So the Earth is rotation, but the two axes are pointing always in the same direction. And then this is only the cross product of these two. Okay, now we are in orbit. We have different ways to define our movement in orbit. This is one example. For example, an orbit is a plane. We are rotated always on this plane, and the Earth is rotating below us, but it has no effect on orbit. So we could define, for example, Z is pointing to the center of the Earth, Y is pointing orthogonal down to the orbit plane, and X is the cross product of these two. And here we have a difference. I cannot say this is my velocity vector because they are not orthogonal. Or I can do it different. I could say, okay, X will be my, okay, X will be the speed, the vector speed of my satellite, in which direction I am moving. Then I could say Y is orthogonal to the orbit plane, and Z is the multiplication of these two vectors. So you can see there are many different ways how to define my coordinate systems, according to movements where the Earth is, and my orbit maybe relative to the Sun too. Okay, and this is, if you want to take a look to the slices. Here I have a more precise definition of these different types of parameter of orbit, not orbit, of coordinates definitions. Okay. Wow, so many. Okay, and now let's come back about this position, attitude, translation, rotation, pose, and delta pose. Do you remember? Position is related to attitude, and this is not difficult to compute. We will see it's only addition and subtraction of vectors, three-dimensional vectors. This is not difficult to compute. Then we have attitude related to rotations, and this is much more difficult to compute. We will need at least 2 movies to compute the relationship from attitude and rotation, or from rotations to attitude. And then at the end we have the pose, which is nothing more than the composition of position and attitude, or delta pose, rotations, and translations. Okay, now let's see. We were talking about position. And as I asked you at the beginning of the movie, where is my position? You say the position of one point of me. And do you remember? So is position defined. We have our reference coordinate system, and we have one point. But now we have something bigger than one point. For example, an aeroplane. And we want to know where is the aeroplane. And maybe we get a precision of 1 centimeter. But the aeroplane is much more bigger than this. It's maybe 50 meters times 50 or 80 meters. And maybe 20 meters from the bottom to the top, or only 10 meters. It doesn't matter. But there is much more than one point. And then the question, which shall be this point? At the beginning we said, okay, the center of gravity will be a good option because we are computing rotations and the rotations are around the center of gravity. But now let's take another example. We are close to landing, so we would like to know our position relative to the runway. Okay, what shall be this point when I said where I am and one point of the runway? Maybe out in runway you shall say the position of the runway shall be the center of the beginning of the runway. So I know the position relative to this point where I shall target. Actually, it's a few meters in the front. And in aeroplane, then the center of gravity is not a good idea anymore, because the difference between the center of gravity to the landing gear is maybe 10 meters. So when you think another 10 meters to go, and then we have a hard landing, because we were already on ground, or maybe too early, outside of the runway. That will be very bad. So maybe in this case, we shall use the landing gear, the front gear, and not the center of gravity, which is here. But now, how can we compute the position of the center of the landing gear? Up to now, we have been working with the center of gravity, or maybe we have a GPS receiver, not only GPS, let's talk better from GNS, because the GNSS, because we have much more than just give GPS to compute the global position. The GPS from USA, Galileo from Europe, GLONASS from Russia, Compass from China, and some other. So let's talk about GNSS. Now, GNSS. Okay, if we compute the position using GNSS, we compute the position of the receiving antenna. And the receiving antenna shall be on the top of the aeroplane and maybe in the back. So the difference between the computed position from GNSS or GPS to the landing gear can be several meters. Maybe 10 meters down or 20 meters down, and maybe 50 meters to the front. Okay, from the first glance you will say, that's not a problem. It's only a subtraction. We subtract 10 meters and then we know the position of the front wheel. This works only if my aeroplane is totally horizontal. If my aeroplane has an inclination, then it's not only subtracting, it will be more than that. Or maybe my aeroplane is flying like this, then the front wheel could be even higher than the receiving antenna. So you have to consider the rotations too. And this will make everything much more complex. This comes later. Okay. And now let's talk about attitude. The attitude is relative to something, so it's the angle between two coordinate systems. For example, the angle between Z and Z, Y and Y, and X and X from my reference and my body coordinate system. Okay, let's try to define what is my attitude. Let's assume I have this aeroplane and I would like to define what is the attitude of my aeroplane. I will take you as reference, so my aeroplane is looking exactly to you. So I could say this is the attitude of my aeroplane if I define this vector, the x vector. The x vector is looking to you. And with this I define the attitude of my aeroplane. Exactly like this, I will take this and I will say the yellow vector is pointing exactly to you, and then I have defined the attitude. Is it true? It is only part of the attitude. It's ambiguous because I could rotate in this direction. This vector, the x vector of the aeroplane, is still looking at you, but I am rotating and I was not able to detect this other rotation. So to define the attitude, I need at least two vectors. Let's say the x vector is pointing to you and the y vector is looking to the bottom. So I have defined it already. There is nothing I can rotate or move without detecting this with these two vectors. And now we have the questions. Okay, we were talking about two vectors, but my coordinate system had three vectors. And we are talking about the deviation from this axis to this axis, from this axis to this axis, and so on. So we need three vectors. What we have defined only two. I hope you remember if I have two vectors, I can just use the cross product or vector product, and I will get an orthogonal vector to these two vectors. So if I have two vectors already, it's not a problem anymore. I make the vector product of this, and then I will get the missing vector. Then I have already three vectors, and I can compute the deviation from every of these to any of these. Okay, and now I have a nicer example. A case which we have in space missions every time. I would like to know my position relative to the center of the Earth, or maybe my positions relative to Würzburg. Würzburg is somewhere here. Maybe in Würzburg we have our antenna, and I would like to communicate with the satellite, and the satellite shall point its antenna to Würzburg in order to communicate with me. Okay, he shall know where is Würzburg. And that is somehow difficult. Because, for example, if you take a camera, you shall be moving the camera until you find Würzburg, and it's really difficult to detect. Or even to detect the center of the Earth from a satellite is really, really difficult. I don't know how. Or, well, I know how, but too difficult. There is something which is more easier. We have stars. And we can always look at the stars from a satellite. And if we take a photo of the stars, a star is only 1 point. And exactly the same like I did before, I am pointing this vector to you, and then I know my attitude relative to this vector. I can do this to the star. So I could say this vector is looking to this star, and then I have defined my attitude, but I am missing one vector. But we have more than one star, then I can use two vectors. One vector is pointing to this star, and other vector is pointing to these stars. And if I have these two vectors, then I can compute my attitude relative to the stars. I will say this is an inertial attitude. Okay, but I wanted to know my attitude relative to the Earth, to the center of the Earth, or to Würzburg. But I can do exactly the same from here. I can see my position, angular position, relative to the stars, and then I can compute my attitude. And then I know my attitude relative to the stars. And the nice thing is I do not need to see the stars because I know where they are. We have a star catalog, and we know what time is it, and then I can compute my position relative to the stars because I know everything which I know to compute this. So I know my attitude relative to the stars, and the attitude of my satellite relative to the stars, and then to know the relative attitude from the satellite to Würzburg, I just need to subtract these two attitudes. Well, the subtraction of attitudes is somehow more difficult than just subtracting x minus x, y minus y, and so on. You will see we will use matrix transformations with matrices or quaternions, which is much more complex as addition and subtraction. But this comes later. I wanted just to say we can go another way to compute the relative attitude from one device to other device. Okay, then something more. What shall be our reference? Not only from attitude, but from position too. Let's assume I would like to go from the Earth to Neptune. Okay, which coordinate system shall I use? This here is my body coordinate system. And this is one reference coordinate system attached to the Earth and another coordinate system attached to Neptune. Okay, of course, as long as I am on the Earth, I shall use a coordinate system which is moving and rotating together with the Earth, including rotating. This is the SF coordinate system, rotating together with the Earth. Then I depart from the Earth, and when I arrive in orbit, then I can ignore the rotations of the Earth. I can switch to SF. So my coordinate systems will be moving together with the Earth, but will not be rotating together with the Earth. Then I depart from the Earth and I begin flying Neptune. To keep using the Earth as reference coordinate system could be somehow very complex because the Earth is moving away. And my position shall not be relative to the Earth, but my way relative to Neptune. Maybe now I shall change with a coordinate system which is relative to the Sun. And maybe my attitude relative to the stars. So I can have a star inertial attitude system like I mentioned here. And if I want to know my attitude relative to the Earth or something else, I can compute in the same way as I said it before. Okay, then we are continuing our flight, and then we come close to Neptune. When we are close to Neptune, then we shall switch again. Then I don't need the Sun as relative navigation, but Neptune. So I am going to use this coordinate system relative to Neptune. Maybe for both things, for attitude and for position. And what do you think? Do we still need the coordinate system of the Earth? Now we are in orbit in Neptune, so we can forget about the Earth. No, it's not, because we want to communicate with the Earth. So I have my antenna, and in order to communicate with the Earth antenna, I have to point with my antenna to the direction of the Earth. Then I have to know where is the Earth and in which direction, which attitude. I need both position and attitude, and then I can compute in which direction I shall move my antenna to point in this direction. Okay, and now we have a combination of both things, my position and my attitude. 3 dimensions position, 3 dimensions attitude, 6 degrees of freedom. And this is going to be used to point vectors, to point antennas, and everything, anything else. Okay, but now let's say a few words about translation. Translation is really not difficult. It's just adding and subtracting vectors. For example, if we are moving from one point to other point, and I would like to know where I am now, then I have to use to add the 3 coordinates of my old position plus my movement, and then I will get my new position. So, and this addition of vector is just adding the 2 x components, the 2 y components, and the 2 z components. Oh, I see it here. Here is a mistake. This shall be y and not x. So I can compute movements and distances. Let's take an example. Let's take this point. And this point was attached to this coordinate system. That is my body coordinate system. And then my body coordinate system has moved from here to here. That is my new position of my body coordinate system. And this is the position of my point, which relative to my body didn't change. Okay, what is now the position of this point relative to my reference coordinate system? Just add what I know, the old position, which is a 3D vector, plus this movement, which is again a 3D vector, then I'm going to have my new position. And everything very nice and very simple with this, it is permutative. If I have a chain of translations, I can just add them in any sequence. If I'm moving like this and then like this, it will be exactly the same position like if I move like this and then like this. So I can interchange the sequence of additions. But be aware, we can do this with translations, not with rotations. With rotations, we have to keep a fixed sequence of transformations, of rotations, else we are going to land in other position, in the ground position. Okay, now the distance between 2 points. Here there is something which you shall take care. If I would like to compute the distance, you will say, okay, it's very easy, the distance, the difference between the x coordinates square plus the difference between the y coordinates square, and the same with z, and then the root from this. But please, they have to have the same reference, because it has a position relative to this coordinate system, and it has another position relative to this coordinate system. Maybe it's the same, but the bodies of the coordinate systems are not at the same position. So first you have to transform this to a reference coordinate system, both of them. And when they are in the same coordinate systems, then you can compute this formula, else it will be wrong. Or maybe you can compute from here to here, and then from here to here, and then you have both this distance relative to this coordinate system. So it doesn't matter which coordinate system you are using, but you have to use the same for this transformation. So if you know exactly the same, the position of this body and the position of this point relative to this body, then just add these 2 vectors. And exactly the same, you add these 2 vectors, and then you get the vector A, and here you get the vector B. And then you can just make the subtractions which I mentioned before, xi minus xb squared, and so on till z, and then the root from that. Okay, and this is the magic of translations, which is really not difficult. The next point, the next two slices are not slices. The next two movies are about rotations, which is, sorry, but much more complex. Then see you in the next movie.